Okay, then welcome again after lunch break. Last lecture of the day. In this lecture, we will talk about structural integration of smart materials, and we can integrate the transducers in carbon fiber or in general fiber reinforced plastics. And therefore, we will have also a very brief introduction to fiber reinforced plastics, fiber reinforced composites, since I think not all of you are familiar with these kind of materials. So we are here, structural integration of functional modules, and after T then you will have the third lab of the short course. Who of you is familiar with composite structures? Who work with it? Yeah, you too. Okay, so maybe 20% of the course, something like this. So the learning objectives of this lecture are that you can explain why fiber reinforced composites are used at all. Then that you can identify different scales of analysis or different scales to look at fiber reinforced composites, that you're familiar with common fiber and matrix materials, and that you know 3 different ways in which functional modules or transducers we had in the last lecture, in the lecture before the last lecture, are integrated into these kind of structures. So we will first have an introduction to fiber reinforced composites in general, then look at different scales, micro, meso, macro scale, and then we'll have a look on the integration. So what do fiber reinforced composites have to do with adaptronics or smart structures? If we want to have systems with high level of integration, so here is a more mechatronic system. Here we have a surface applied actuators and sensors. But if we want to have higher levels with integrators, actors and sensors, then we can't do it with metals that easy. So we use, or it's a good combination with fiber reinforced plastics. And at the end, we will have a look at different approaches to integrate these piezo composites or these functional modules into the laminates. Fiber reinforced composites are very much used in aircraft construction. In this diagram, you can see or each dot or point in the diagram is a different aircraft type. The filled ones are military aircrafts, and the round ones, the circles, are civil aircrafts. And here's the year of entry into service. So first entry into service of these type of aircraft. And here's the composite content in the structure in weight percent. And you can see a trend that the newer the aircraft is, so later introduction to service, the higher the composite content is. And military aircraft tend to have higher composite contents since you have smaller numbers to build, and composite structures may be more expensive than metal ones, so therefore it's more affordable for military aircrafts. As an example, we have here the Airbus A380, which is not in production any longer, but in different colors or in different colors it is coded from which materials the parts are made from. So the blue structures are made from metals. The orange ones are made from GFRP, so glass fiber reinforced plastics. And the purple ones are carbon fiber reinforced plastics. And the yellow ones are glare. Does somebody know glare? What do you know what it is? Yeah, it's but not only glass. Yeah, it's a fiber metal laminate made from GFRP, glass fiber reinforced composites, and also aluminum layers to have an improved fatigue resistance of aluminum structures. And do you know why we have in the fuselage different approaches regarding the materials in one aircraft. Airbus is a company with factories distributed all over Europe, also USA and China, but mainly Europe. And these sections here are developed together from German and Dutch engineers. So they are made of glass, and these sections are coming from France, and they wouldn't use glass. They stayed with, let's say, traditional aluminium structures. And yeah, also Boeing aircraft 787, Dreamliner, which has even a higher composite content. So the whole fuselage here in purple is made from composite structures. In our diagram, Boeing 787 is here, about 50%. And let's look up, here's the A380, maybe around 22, 23% of weight percent carbon fiber. Carbon fiber reinforced composites are also used in automotive industry, for example, in monocoques, but only for, let's say, sports cars or low production volume cars due to the costs. This was a small series car from VW, where the goal was, it has a diesel combustion engine, and the goal was that it only takes 1 liter per 100 kilometer. So it is a really light structure, and I worked on this car when I was a student in an internship and during my thesis at VW. This is a leaf spring, traditional made from metals, but you can also make it from GFRP. It's used in some smaller trucks, commercial vehicles, and also tanks for example, CNG, so pressurized tanks, pressure vessels. And this is a structure from the back seat in an Audi A8, so large Audi car. We also have fiber reinforced composites in other industries, sports equipment, bicycles. This is a shaft from a wind turbine, also made from CFRP. This is the front element of a train with the large doors where the connection to other trains is hidden behind. It's also made from GFRP. And here we have a prosthesis to replace a foot, for example, from the German manufacturer Otto Bock, who is maybe quite famous also in Paralympics. So what is a fiber reinforced composite material? We have many of you may have seen these kind of pictures. We have fibers and matrix, and this forms the fiber reinforced composite. So similar to the composite we had before, but we don't have piezoceramics now, but glass or carbon or natural fibers together with the matrix, which is similar to the matrix from the functional elements, and they form the fiber reinforced composite. Why are fiber reinforced composites used? Who knows this kind of diagram? Specific strength is on this axis and specific modulus is here, called Ashby diagrams, I think. There you have the strengths over the density and also the modulus over the density. And can you spot the composites in the diagram? Yeah. Here, the brown ellipse are the composites. Here's CFRP. Here's GFRP. Here are elastomers. We have foams here, unreinforced polymers, and metals are here the red area. So composites compared to other materials have very high specific strengths and also very high specific modulus, and therefore it's an interesting material to design and manufacture lightweight structures. this is a similar diagram, but now the axes are exchanged. So we have here the specific modulus, modulus divided by the density, and here's the specific strength. And here you can see that metal materials have nearly the same specific properties, steel compared to aluminum compared to titanium, and over here we have different types of carbon fiber, intermediate modulus carbon fiber, high strength carbon fibers, and high modulus carbon fibers. Here are aramid fibers, and here are glass fibers. So we really want to use these fibers to have a high performance material. But this is only the fiber properties without the matrix material. What are then the functions of fiber and matrix? Most materials exhibit higher strength in fiber form, and in part also higher stiffness than in compact form. So even if you would produce metal fibers, they would have higher strength than the bulk material. And the functions of the fiber are, or the main function of the fiber is carrying the loads, so delivering the high stiffness and strength for the material. And the matrix fixates the fibers in the desired arrangement. It's keeping the fibers separated so they don't rub against each other. They serve as a load introduction into the fiber. So you have to bring the loads into the structure, which is done also by the matrix. And they're taking over the mechanical loads when you have loads transverse to the fiber, so not in fiber direction but perpendicular to it. Then the matrix also carries load as well as under shear. And under compression, they prevent the fibers to buckle, to have a stability failure of the fibers. And fiber reinforced plastics are often laminated from different layers, which are stacked on top of each other, and they act also as a force transmission between these layers. Yeah. And if you have a tough matrix system with some thermoplastic parts in it, then it also can act as a crack arrest. And you also protect the fibers against environmental influences, UV light, chemicals, and so on. So what are common fiber types? We already had glass fibers and carbon fibers. We also have aramid fibers, you mentioned, and some other synthetic fibers like PBO fibers, Cylon is the trade name, or polyethylene fibers called Dyneema. Further fiber types are natural fibers, basalt fibers, quartz fibers, aluminum oxide fibers, or silicon carbide fibers, but they are not that common. I think the most common ones of these are natural fibers. For example, from flax, hemp, rami, jute. Looking at the matrix materials, I think the most common matrix material are epoxy resins, which can cure under room temperature or at elevated temperatures. Unsaturated polyester resins, vinyl ester resins, phenolic resins. Elastomers are rarely used because they don't have that high properties. And we can also use thermoplastic semi-crystalline like PP, PA, or PEEK, or amorphous thermoplastics like polystyrene, PS, or polycarbonate. Can you say what these structures are compared to the names here? So what is this structure stands for? So this is a strong cross-link. This is the thermoset material. The elastomer here, similar to the thermoset, but only weakly cross-linked. We have here the amorphous thermoplast and thermoplastics, and here is the semi-crystalline ones with these crystalline regions, and amorphous regions around, like the PVDF material we had with the polymer-based functional materials. If we look at fiber-reinforced plastics have a hierarchical structure. We can look at the microstructure, the mesostructure, and the laminate, which is the macro scale. On the microstructure, we have the fiber and the matrix around. The fiber has a diameter of roughly 10 micrometers, depending on the fiber type. So we have the matrix, the reinforcing fiber, and an interface between these two. Then next level would be the single ply, which is between 0.1 and 0.5 millimeters in thickness. We can have it as continuous fiber reinforcement with unidirectional fabrics, or non-woven, so meaning that we have only fibers in one direction. And we could also have a woven fabric, so that two directions are woven into each other, in this direction and in this direction, for example. And we can also have long and short fiber reinforcements. But for really load-carrying structures, like aerospace structures, most of the time we use unidirectional continuous fiber reinforcement or woven materials. And with the single plies, we then can build up laminates, so stack the individual plies on top of each other with differently oriented single plies. And then for monolithic materials, we can divide between unidirectional or multidirectional materials. Unidirectional, all plies have fiber orientation in the same direction. Multidirectional, for example, like here, 0 and 90 degrees. And then we can also distinguish hybrids, fiber metal laminates like Blair. For the laminate, we can then have a look at the laminate stacking sequence. The benefit or the advantage of fiber reinforced polymers is that you can tailor the stiffness of the laminate to the load application in the use case. So you can have if a structure is not loaded equally in all directions but has a major load path, then you could orient more fibers in this direction and so adjust the stiffness in this direction that you have more load carrying capability where you need it. And this is because we have a high stiffness and strength in fiber direction. So in this direction, in this direction, in this direction. And a low stiffness and strength in transverse direction where the matrix takes the loads. And an example laminate stacking sequence is 90 plus minus 45 degree 0, and then the S stands for symmetry, so it's this kind of a layup where you have 90 plus 45 minus 45 0, and then symmetric 0 again, minus 45 plus 45 90. And laminates can be highly autotropic or quasi-isotropic, like for the example laminate stacking sequence. So you can build really orthotropic laminates with higher stiffness in one direction, and this laminate with, let's say, all directions covered would be quasi-isotropic, so behave similar like isotropic material, for example metal. So how do we approach fiber reinforced plastics? We have this microscale. Unfortunately, it's German again on the slides, but I will walk you through. On the microscale, when we look at fiber and matrix and also the interaction, then on the mesoscale we have the single ply. From this, laminates are made. These laminates we use for subcomponents and then have components like this fuselage barrel and then maybe the overall structure. And I took these slides from my finite element course where we teach finite element for fiber reinforced composites, and there we start with the microscale, have models for this, then on this level, and then later on the macro scale. Therefore, I have this slide up, and I didn't mention yet in these slides we have E for the Young's modulus, so not the Y again, because I took the slides from a different course. So if you look at the micro scale, we have a heterogeneous material. For example, carbon fibers are anisotropic, or glass fibers are isotropic, and in isotropic matrix, we need the properties of fiber and matrix to describe this. If we want to go to the mesoscale, then we have an homogeneous material. So we don't look at the fiber and the matrix, but the single ply overall. But then it is transversely isotropic, for example, so not isotropic. And on this scale, we have a description of the whole ply, and then on the macro scale, we look at the whole laminate, which is also homogeneous and anisotropic, but then we need the properties of the whole laminate. So then we need a description of the stiffness of the laminate. This is an example micrographs for the microstructure. This is prepreg material CFRP. The matrix is 8552 with an IM7 carbon fiber. And just to get you an idea how evenly the fibers are distributed, these from here to here, it's 1/8 of a millimeter roughly, so 0.125 millimeters. And I think this is a rather good and evenly distributed material. So just to get an impression. To go to the mesoscale, we use homogenization methods. So we need tools to go from fiber and matrix properties to the properties of the single ply. And this can be done, for example, energy-based with some analytical methods by Vogt and Reuss, semi-empirical models, or FE-based. We won't go into detail about this, but you can, or only in this model from the idea, there you assume in the Reuss model that you have same stresses over the cross-section, but different strains. And in the Vogt model, you assume that you have the same strains over the cross-section, but different stresses. Here the fiber is stiffer, so the stresses would be higher than the matrix. And the Vogt model is a good approximation to get the properties in fiber direction, and the Reuss model is a good rather good approximation for the transverse direction. If we look at the material properties, some different glass materials, so all glass fibers, but different types. They are between 55 and 86 gigapascals, Young's modulus of the fiber, Poisson's ratio of 0.22, and tensile strengths between 1,650 and 4,500 megapascals, and densities around 2.5. If you look at carbon fibers, they have similar tensile strength, lower densities than the glass fibers, but far higher Young's moduli. For the high tendency fiber, 230 gigapascals, up to the ultra high modulus fiber, UHM, 450 gigapascals. And also natural fibers, we have, for example, flax, jute, sisal, or banana fibers, which have, far lower properties, 25 to 37.5 gigapascals, but lower density even than carbon fibers, but also lower tensile strength. So the best natural fibers, I think, can be compared to the worst or lowest performing glass fibers. we have a look at the material properties of the matrix materials. For example, we have the epoxy resin, cold curing and heat curing or hot curing. Then we have around 3 gigapascals in modulus and a really low strength between 35 for polypropylene and 90 up to 90 for the epoxy. And from this you can also see that the matrix material is really the, let's say, secondary, not load carrying material, because the load carrying capabilities are delivered by the fiber. And densities are around 1. Again, an example for the 8552 IM7, we have the material properties of the fiber and the matrix. The fiber has 276 gigapascals in fiber direction, but they are also anisotropic. So the fiber has in fiber direction a higher stiffness than transverse to the fiber direction. This is the second modulus here. And then the modulus of the matrix, 3.7 gigapascals, and a fiber volume fraction of 0.6, so 60% of the volume are fibers and 40% of the volume of the composite is matrix. And I've calculated from these values with the rules of mixtures from Vogt and Reuss the modulus in fiber direction and transverse to it of the composite, and you can see that Vogt and Reuss for fiber direction give really different values, and Vogt is close to the experimental values of 171 gigapascals, and Reuss is maybe, Vogt in this case is also closer in the for the transverse direction. Yeah. Sorry? I didn't get it. So what? Halpin psi. Yes, I have it in the Halpin psi model in the original slides from the other course, but I removed it for this compact course. Yeah. So what she was asking is, there's a Halpin psi, a semi-empirical model, which has some correction parameters so that you can correct the Vogt and Reuss models to the experiment. So then with this you are closer to the experimental values with some additional parameters. So a semi-empirical model also for the homogenization. Yeah. So without going into detail into the equations, we are now on the mesoscale, having our properties for the single ply. And now the question is, how do we go to the macro scale? First, we have to take a look at the plane stress state. Who is familiar with plane stress conditions? I think most all of you maybe. So we assume that we have very thin components and can neglect the stress and thickness direction, from which it follows that also the shear components, the out-of-plane shear components, are 0. And then our compliance equation, or the materials equation, reduced to only 3 components and not 6 for full 3D. And the classic lamination theory we will have a look at later on assumes also this plane stress conditioned. So we have a description for the stiffness of a single ply, looking like this with these 5 components. The assumptions of the plane stress state don't lead to 0 strains in thickness direction. So we assume only that the stress in thickness direction is 0, but not the strains, because they arise from the coupling of the normal stresses. So we have a 3-dimensional strain state, even if the stress state is 2-dimensional, and we can calculate it afterwards with these equations. And we need in terms of engineering constants, the modulus in 1 and 2 direction Poisson's ratio, and also the shear modulus and the out-of-plane Poisson's ratios for this. So this would be a description of the, again, 8552 IM7 material for plane stress conditions. So now we are going to the macro scale, and we will only have a brief look at classical lamination theory to see how we can get the stiffness of the whole laminate from the properties of an individual layer plus the stacking sequence. And in the classic laminate theory, we determine 3 different stiffness matrix: the membrane, the bending, and the coupling stiffnesses of a laminate. So we get the so-called ABD matrix. We assume that strains and curvatures are at the mid surface of a laminate, and use the engineering constants of a laminate. So how does it work? Very briefly, without giving you the equations, we have our individual plies where we have the properties from. Then we have the laminate stacking sequence, which we use the fiber orientation to transform the stiffness matrix and rotate them according to their orientation in the laminate. And then we assume that we have strain compatibility, so that all plies are ideally bonded to one another, and they can't, so all have the same strain, they can't detach or slide against each other. Assumptions of the classic lamination theory are that the laminate is thin, so the thickness is small compared to the other directions. That we assume that the laminate thickness is also constant. We assume a plane stress state because we have the thin-walled structure. And we again have the Bernoulli assumptions like we used in the last lecture, that we say cross-sections remain plane and are shear rigid in the thickness. Deformations are small. Strain compatibility, the individual plies are perfectly bonded to each other, and the plies are homogeneous and linearly elastic, so we don't assume any plasticity or nonlinear effects, and also no damage at this point. And we assume that the laminate lies in the XY plane. This is the in the coordinate system. And then we build up our laminate like this. We have here the mid surface. We start at the bottommost ply and then stack the plies on top of each other and have a Z coordinate for each ply in the laminate, independence of the mid surface. And then we have we can use it to calculate stresses and strains of the laminate with respect to the mid surface, but we can also transform it back to the individual stresses in the individual plies. And the result then of the classical lamination theory is this ABD matrix, where we put in the different strains, and we get these are the external loads, the normal loads, the shear, no, not the shear, the bending moments, and the twisting or twist moments. So the CLT process, we go into the CLT process with the engineering constants of the individual plies. From this we build the plane stress stiffness matrix. Then we have the information about the angle of the individual ply in the laminate. We transform the stiffness matrix using this angle with some transformation equation and matrices, and then we add the information about the Z coordinate. So where does the ply, or where's the ply located in the laminate, in the middle or outside? And with this, then we get in the end the ABD matrix, which is then a full description of the laminate. And by looking at the ABD matrix, we can learn something about the behavior of the laminate. These A matrix, which is the membrane stiffness, yields the stiffness in the, so AY11 is the stiffness if we pull the laminate, then have normal forces on the laminate in this direction, and how is the stiffness also in this direction. A12 is the transverse coupling, so Poisson's ratio. When we pull it, then we also have a contraction here. A16 is the coupling of normal forces with shear, and so on. We have here on the diagonal the plate stiffness. So how does it behave under bending in the different directions? And what is, I think, interesting is these B matrix, which is the coupling matrix. Normally the aim is to have the B matrix 0, that you have no coupling effects, because the coupling effects lead to some interesting behavior. If you pull, for example, the laminate, then it would bend in this direction, or if you pull in the other direction, then it would also bend, or it would even twist. But why do I have the slide here? If we apply surface actuators, functional modules on laminate, and we have a laminate with a B matrix, so coupling effects, then we could use the transverse actuation, the in-plane actuation of the actuator to, for example, get to an bending of the laminate. So in the combination of the actuators with an engineered ABD matrix could give us some interesting overall structures from the actuation behavior. So this was really a rather brief introduction to fiber reinforced composites without many equations, but I hope you get a glimpse on fiber reinforced composites. And now we have a look at the integration of functional modules in these structures. We can integrate functional modules into a laminate, but this would disturb the load path and reduce stiffness and strength, because at least they are less stiff than our carbon fibers. And the objective is that we keep these reduction in stiffness and strength as small as possible. So we are looking for these kind of integration levels. And for this, we have 3 different configurations which are basically possible. First configuration would be that no plies are cut. So you build your laminate with the individual plies, place the functional module or the transducer, and then just put the other plies on top of it. Then you have here some kind of resin pocket, which could also be a weak point in the laminate. The second possibility is the integration with a complete cutout. So you cut all fibers in thickness necessary to integrate the functional module. So the overall thickness of the laminate will not change. And the third option is the integration in a partial cutout, where you cut only a few fibers and some are going around the transducer. And in this case, 0-degree fibers are not cut. You have an idea why we maybe cut the 90 degrees or the 45-degree fibers and not the 0-degree fibers? If the load, the main load path is in this direction. Yeah, so the 0-degree plies then give us more stiffness and strength than 45-degree plies, and if we won't cut all, then we may choose the 0-degree plies to go through and be not cut. Before we have a deeper look into this. One example of integration, there was one example structure also at German Aerospace Center before I joined German Aerospace Center, so I'm not deeply involved in this, but there was a fiber reinforced plastic bogie, so the wheel assembly of a train with integrated actuators. It was made from GFRP in combination with surface actuators, and the goal was to have an adaptive vibration control of the structure then. So coming back again to the different integration possibilities, this was investigated with simple tensile tests again, but these tensile tests are different than the ones we saw before. There we did a tensile test only on the functional module itself, so no FRP structure, and here we have tensile specimen made from CFRP with the transducer integrated in the different ways, and we have strain gauges also here and here, so in the undisturbed cross-section and in the disturbed cross-section. And it was a quasi-isotropic layup, 16 plies, 0 plus 45, 19, minus 45, 2 times, and then a symmetric layup. And also reference specimen without piezo composites integrated. And the goal was to assess the influence of the integration of the strength and also on the piezo composite. How did it look like in a micrograph? So these are 0.45 millimeters. We have here the plies from the fiber composite, the 45-degree ply, and here's the 0-degree ply. With again here 45-degree ply and 0-degree ply, and here in the middle is the functional element. We have here the piezo ceramic in the middle. Here's the contact mesh we apply to contact the electrodes, and the insulation also with the thermoset resin of the functional module. And then we have a symmetry here, so same on the other side. The option without plies severed, so resin pocket here, but no plies cut, looks in real like this. You have the functional modules here, and again here and here. So this microsection is in X direction, longitudinal direction. This is in the transverse direction, and you can see the fibers in the middle going more or less straight, and these have a curvature to go around the functional modules. And here are some resin pockets where you just have the matrix material of the fiber reinforced plastic without the fiber reinforcement. Then the second option was the complete cutout, which you can see here, functional module and nearly the same height, so 3 plies were cut to have the same thickness of the laminate in total, not thicken it, just to the functional modules, some plies going through this and this one, and here you have the partial cut plies, and for the scale, these small white bar is 400 micrometers. Then they were tested in a UTM, tensile testing machine. This is one test example or one representative result of the without any cutout. Here's the fractured tensile test. And we have here a stress-strain diagram where we can see the strain in the integration area and the strain in the undisturbed area. So strain from the strain gauge here, strain from the strain gauge here, and also the piezo signal. And you can see that the piezo signal fails early. So here the piezo might have failed, but the structure itself is able to bear more loads before you have the failure of the composite itself. And in the undisturbed area, the stiffness is higher than in the disturbed area, because you have the weaker material in between. If we look at all specimen, here in the diagram, Young's modulus, complete cutout, no cutout, partial cutout. And we also have for reference applied actuators, so just bonded on top, and reference specimen with any functional modules at all. Then you can see that in cross-section 1, cross-section 2 is the higher modulus. It's the undisturbed region. It's nearly the same, so not affected. But the cross-section 1, where the strain gauge is applied in the region where the functional modulus is, the functional module is, the lowest stiffness is by the complete cutout, and the partial cutout has the lowest impact on the stiffness, but even the application leads to a lower stiffness. And we have here the same for, here are also the breaking forces, or the fracture forces indicated, which are also the highest for the partial cutout, but comparable to the without any cutout at all. And yeah, for completion also the failure strain. So the best results were achieved in the tensile test when we integrated into a partial cutout, so that the load-bearing 0-degree fibers remain intact. But owing to the distance that, to the smaller distance to the neutral fiber, or the mid-plane of the laminate, the work capacity of the integrated functional modules is lower than the one applied. So if we have here again our work diagram, displacement and blocking force, and this is the one with the applied actuator. It has the largest distance from the midplane of the structure, therefore the work capacity is the highest. When we don't cut any layer, then we have the lowest work capacity, and the complete and partial cutout give nearly the same free displacement and blocking force. So to sum up, materials in fiber form exhibit higher strength, and in some cases also higher stiffnesses than in compact form. Fiber and matrix have different roles in the fiber reinforced composite. Fibers bear the loads. The matrix material is in, let's say, helping structure to introduce the loads and also to keep the fibers in place and to protect them. We can integrate functional modules in different ways. We looked at 3 different ways, where the partial cutout yields the best properties or the best trade-off with respect to stiffness and strength. This is again, the work capacity of integrated modules is lower compared to the one with applied modules, because the smaller distance to the midplane. And with this, I'm at the end for this lecture. Do we have questions? Not at the moment. Okay. Then we now have tea break, and afterwards, so 4 p.m. We have the